So here's an example of working with confidence intervals in R. We're going to calculate some confidence intervals. We're going to calculate multiple confidence intervals for the same data set. Then we're going to see how we see variation in those confidence intervals based on the sample means. Hopefully all of that will become a little more clear as we move on. So what I'd like to do is work with what's called the youth risk behavior surveillance system, or YRBSS data. And this is a survey that's run by the CDC to assess the effects of different behaviors on risks of negative outcomes for youth. And you can get a lot more information on the CDC page for this, and we'll show a link to it in just a moment. But this data set, part of this data set, comes in a book, or comes associated with a book called Open Intro Statistics, which I mentioned in class. And because of that, if we download the Open Intro package, then we can get access to this data set, or the data set we're going to use today. So first off, let's do the install packages. We're going to install the Open Intro package. So we install Open Intro. Takes a few minutes. Okay, here we go. Installed. I'm just gonna remind myself not to run that in the future. Okay, so now we have the package downloaded. So let's load the Open Intro package. So library, Open Intro. Run that command. Now we have Open Intro available. So let's get the YRBSS data. And to do that, we're going to do data YRBSS. If we go over to our environment, we see, as we've seen with data sets in the past, it's YRBS and it says promise, which means that once we call on this data set, it'll be available. So for example, if we do head YRBSS, we see the first 6 lines of the data set. And just looking at the head, we see there's this column of age. So these are the ages of the students that have been surveyed, their genders, their grade, whether they're Hispanic or not, their race, their height, their weight, whether they've worn a helmet while riding a bike in the last 12 months, whether they text while driving in the last 30 days. So you can see a number of different measures or questions that were asked. When we get more information on the YRBS dataset, we could just do $YRBSS. And here we get our basic R help file, which includes help on data. So the data includes the data frame of 13,583 observations of the following 13 variables. And again, the source is the CDC's Youth Risk Behavior Surveillance System. So if you click on this link, you can go over and get a lot more information about this particular data set. Since we're looking at the data, why don't we get a summary of the data? You can see summary YRBSS. And there we go. So we're going to be working with the height data today. I just want to point out that there are about 1,000 NAs in this data set. So those are 1,000 entries of the 13,000 plus entries that have no value for height. So first off, let's calculate the population mean height. So this is the mean for all of our survey data set, all 13,583 points. So if we do mean, YRBSS, and then height, we see it returns a value of NA. That's probably not what we were looking for. So what do we have to do? We have to remove NAs. So mean, YRBSS, height, NA.RM equals true. And that's going to remove the NA values. What I want to emphasize here is that this is the population mean. Our population is all individuals who took the YRBSS data survey, or YRBSS survey. So this is the true population mean for height of this data set. Let's save this as a new variable. So we'll call it YRBSS height, HGT is what I'm going to use, pop mean. For now I'm just going to call it pop, YRBS height pop. And this is going to be mean, YRBSS height, NA.RM equals true. Okay, so let's gather a sample from these data, and we'll use that sample to estimate this population mean height. So we're going to get a random sample from the data set. Sample size is going to equal 10 right now. So I want to make this so that we all get the same values, even though we're going to use a random process. So we're going to set a seed. I'm going to set seed to 623, since that's our course number. And then we're going to do YRBSS samp. Now, just be careful. I'm using YRBS underscore samp. There is a predefined data set called YRBSS.samp. We don't want to use that. We want to use this underscore samp. So what I'm going to take is a sample of the full YRBSS data set. I'm going to use the sample function. And I'm going to sample the values 1 to the number of rows for the full data set, YRBSS data set. And that's my X vector. That's my vector that I'm sampling from. I'm going to say replace equals false and size equals 10. And because I'm basically taking rows, this set of rows and a full set of columns, I've got to add a little comma here to go row column notation. And there we go. I have a YRBSS SAMP of 10 observations. Just to be clear, if I were to run just this sample function, we get these values, these rows. So it's extracting a set of rows from the YRBSS SAMP. So I have my YRBSS SAMP set of rows. What is the mean? What is my sample mean for height? The mean YRBSS underscore SAMP height na.rm equals true. Here we see my mean of my sample is a value of 1.678889. So as we did before, let's save this as a new variable. Sample mean as a new variable. And we'll call it YRBSS underscore HGT SAMP. And this is just our function from above. Okay. Now let's compare these. So how do these compare? These values compare? So we'll first report the population mean, and then we can report the sample mean, and we can ask if they're the same. Do they equal each other? I think we already know the answer to that is no. So there we see our population mean, our sample mean, and it's false that they are the same. So we see that this value of 1.67, this is our sample mean. If we took a sample, this particular sample of 10 values from our data, this is our best guess at what the population mean is. And it's not too far away from what the population mean is. It's not precisely the same, but not too far away. Now, I should note that if we increase our sample size, so let's do the same, we'll use the same set of functions here, or commands. Except for instead of taking a sample size of 10, we'll take a sample size of 100. Now it's 1.704286. So this is sample size 100. And if we did the same thing for sample size 1,000, what we will usually notice, though not always, is that as we increase our sample size, we will get closer and closer to the true population mean. So that's usually true, that's generally the case. As we increase our sample size, we get closer to the true population mean. The sample mean is closer to the true population mean. Depending on the sample you get, that doesn't have to be true for any individual sample, but in general, increasing sample size increases the accuracy of our estimate of the population mean. Okay, so how does this relate to our standard error of the mean? So first off, let's just think about our standard error of the mean process that we've been talking about in class. What I'd like to do is take a number of samples from this data set and calculate a number of sample means. So let's take a bunch of samples, calculate their means, and look at the distribution of those sample means. Based on what we've been doing in class, you should already be thinking about the central limit theorem, which is that the distribution of the sample means is going to be normally distributed, regardless of whether or not our YRBSS data are normally distributed. The distribution of the sample means is going to be normally distributed. And that the mean value of that distribution of sample means is going to be very close to the population mean. But let's just demonstrate that using this R code. So we need to start by making an empty vector to store sample means in. So I'm going to call it samp means. And then we're going to use a for loop. We're going to start a for loop. And we're going to do 100 iteration. It's 100 iterations. Or draws 100 different samples. So for x in 1 to 100. So let's get a sample. And we're going to make our samples size 100 for now. So don't get confused here. We're taking a sample of size 100, and we're also doing that 100 times. So YRBSS samp. We're going to use the same names in here. And basically, we're going to be using some of the same code. So I'm just going to go up here and copy and paste it. Except for I'm going to change this value. There we go. I'm going to calculate the mean of this sample. Don't forget to remove RNAs. And I'm going to add this new sample mean to our vector of sample means. There we go. Hopefully I did this all right, and we can execute our code chunk here. Great. So now we have a vector of 100 of sample means. So these are 100 different, the mean values from 100 different samples drawn from this YRBSS data set, just for the height value. So let's look at what the histogram looks like for this. I'm going use ggplot and do ggplot gm histogram my aesthetic x value equals sample means. Let's try that again. There we go. Okay, so this does not look especially normal, but it's normal-ish. It's at least unimodal, somewhat symmetric. Then we have a couple questions that we should ask here. Like, let's see. What is the mean of our sample means? Well, let's do mean mean of our sample means is 1.690194. How does this compare to our population mean? Remember that we have this value YRBS HTT pop. So those values are very close to each other, 1.690, 1.691. So now we're seeing that the mean of this distribution of sample means is really close to the population mean. Let's ask, what is the standard deviation of the sample means? .01 is the answer there. And then what is the true population standard deviation? This is going to be the standard deviation of our YRBS data set, the height values. Again, we have to remove our NAs. 0.104. So clearly these two values, the standard deviation of the sample means and the true population standard deviation, are not the same. And nor should they be. As we've talked about in class, the standard deviation of the sample means is actually our standard error of the means. And the standard error of the means should be the true population mean divided by the square root of n. So let's just refresh our memory. I'll write this out in LaTeX here, just so we can get the formula. And there we see it. Standard error of the mean equals the standard deviation, the population standard deviation divided by the square root of our sample size. So that would be this value divided by 100. Oh, sorry. Divided by the square root of 100. That makes more sense. So again, our true standard error is going to be really close to what we simulated as our standard error, standard deviation of the sample means. Now we could also have gotten, as we talked about in class, we could have calculated standard error using the standard deviation of our sample as an approximation for sigma. And that would look something like this. Our YR BSS height samp standard error would equal standard deviation of our sample, the height values from our sample, divided by the square root. And I'm just going to be generic here, getting the number of rows of our sample, which is equivalent to our sample size. And then if we look at that value, we see a value of 0.01. So again, our approximation based on using the standard deviation instead of the true standard deviation, the standard deviation of our sample, rather than the true standard deviation of the population, is pretty close. 0.0104 versus 0.01107. Okay, in class, we talked about calculating the confidence intervals. And we use this function, or we use this equation where we said we have the probability of our sample mean, so we'll say y, call it y bar, which is our sample mean, minus 1.96 times our standard error is less than or equal to mu, our true population mean. I'll use the less than equals population mean, so mu pop mean is less than or equal to y bar plus 1.96 times standard E. So why don't we calculate the confidence interval for our sample here. We're going to restart, grab the sample again, and calculate our confidence interval for the sample. So remember we set the seed to 623. Our YRBS samp. I'm going to grab a chunk of the YRBS data. This is the exact same thing as what we've used before. And there we go. Let's just run that whole chunk just to be safe. So our sample mean, let's calculate sample mean. I'm going to call it YRBS height samp. In this case, I'm just going to add that mean tag to it. And that should look familiar to what we had before, this 1.6788 value. Now let's calculate our sample standard error, or the standard error based on our sample. And that's going to be the standard deviation of our sample heights. Again, divided by the square root of the number of rows, or our sample size. Now we can use these values to calculate our confidence interval. We're going to do the upper and lower limits of our confidence interval. And we're going to do 95% confidence interval. So height, samp, mean. The upper is going to be that sample mean plus 1.96 times our standard error. And just to be safe, I'm going to put this in parentheses, even though order of operations should hold. I'm going to do the same thing for a lower bound. I'm just going to change upper and lower. Change this to a minus sign. Change this to lower. And then I'm going to print these out. So if I execute the whole chunk, we see that our upper bound is 1.742886 and our lower bound is 1.614892. So putting this together, if we think about our sample mean, I'm just going to print this out here. The mean from this sample that we drew is 1.67889. Our 95% confidence interval based on this sample is 1.742886 to 1.614892. And that means that we are 95% confident that this interval includes the true population mean. And in this case, if we remember that the true population mean, just refresh our memories of true mean, or let's call it of population mean. Is 1.691241. So this interval does in fact include the true population mean. So, in this case, this estimate for the mean based on our sample has this confidence interval, which does in fact include our true mean. Now let's go one step further and examine multiple estimates and confidence intervals. And what we'll find is if we do enough of these, we're going to find estimates that have confidence intervals that don't actually include that true population mean. So this is going to require me to draw random samples again, as we did earlier, save those means, and calculate the upper and lower confidence intervals. And then we're going to use that to make a figure and show you the confidence intervals and where they fall with respect to the true population mean. So I'm going to start by going and copying and pasting all that code that I use to make multiple samples. So scroll up here. Let's copy all this. We'll make changes as we need to. The first change I'm going to do is I'm going to set the seed at the top again to 623. I'm going to start by making an empty vector to store sample means and upper, lower CI values. And call it samp CI upper and samp CI lower. In this case, I'm only going to do 25 samples. Or draw 25 different samples. And then my sample size is going to be a sample size of 10. As before, I'm going to calculate the mean. I'm going to add that new sample mean to our vector of sample means. And then I'm going to calculate upper and lower CI values. I'm going to make it easier on myself by calculating the standard error. Still have to remove our NAs. Divide by the square root of our sample size. And then our CI, do CI upper is going to be our mean from the sample plus 1.96 times SE samp. And again, I'll put that in parentheses. CI lower, going to be mean samp minus 1.96 times SE samp. And then add these to those vectors that we made. So samp CI lower is samp CI lower plus CI lower, and samp CI upper is samp CI upper, CI upper. All right, so this should work. Let's run that code. Okay, so now we see we have a vector of 25 for our lower confidence interval values, our upper confidence interval values, and our sample means. I'm going to make this into a data frame. So let's plot these confidence intervals against the population mean. I'm going to make a data frame called sampstats df. To make plotting easier. I need to actually number these observations for plotting. That'll become a little bit clearer what I'm doing in a second. But a number from 1 to the length of samp means. I want my samp means to equal samp means samp CI lower is going to be samp CI lower. So basically I'm just making a data frame, a new data frame, where these things on the left side of the equal sign are the column names, and what's on the right side of the equal signs are the vectors that are going into those columns. This might be a little confusing because I'm using the same column names as vector names. So that's my data frame. Let's have a quick look at it. It's my sampstats data frame. Here we see these are my observations column, the sample mean, and the confidence interval values associated with that sample mean. All right, let's make a plot. Let's do, in this ggplot, we're going to use the sampstats data frame. And then we're going to do geom point. And our aesthetic here is going to be x equals samp means and y equals observations. So if we just do that, we see values. These are the sample means. Each little point, each dot is a sample mean, and the y-axis is really meaningless. It's just the number, the observation number associated with that that mean value. Let's add to this. We're going to use a function called geom line range. Our aesthetic is going to be x min equals samp CI lower. X max is going to equal samp CI upper. Our y is our observation. And then I want to add to this a vertical line representing the true population mean. So we're going to do geom v line, or vertical line, and all I need to give it here is the x-intercept, and I'm going to use the YRBSS height population, so height pop. I'm going to make that line red, and then just to be a little bit cleaner, I'm going to use the black and white theme. So let me run this whole chunk, and here's what we see. So each point represents the sample mean from a different set of a different sample set from this YRBSS data. Each line represents the confidence interval based on that sample mean and the standard deviation estimate using that data, using that confidence interval formula. And again, this is a 95% confidence interval. And I should say that we are assuming normality here, so we're using that 1.96 value when we're calculating our confidence intervals. We could be assuming t-distribution rather than normal distribution, but for now we're just using a normal distribution. And what I want to emphasize here is, in many of these cases, our confidence interval does overlap with the true population mean, this red line. But in some of these cases it doesn't, right? So this 24th set of sample data, right? The confidence interval does not include the true population mean. Similarly, for this set of data, looks like the 13th set of data, or the 5th set of data. So just something to think about here is, these data that we collected, this sample of 10 values, we know it is from the YRBSS dataset. We know that these data should be distributed, however, the same way that the YRBSS height data is distributed. Yet, when we look at this sample, our confidence interval does not include that true population mean. So this sample mean, if we use this sample mean to estimate the true population mean, we would probably be pretty off. So I just want to make that point that we know that these data are from that data set, yet because it's only a sample of it, it might not be representative of the full data set. But in many cases it is. So that's all I have for this lesson on calculating confidence intervals in R. Feel free to send me any questions, and I hope this was